Oh, well, hello again. Today I'd like to tell you what happens when your exponent is a fraction. We've seen positive exponents, negative exponents, even the exponent being 1 or 0, but let's talk about fractions next. What might I mean when I write 9 to the power of 1/2? Well, I'm going to try to use a rule I already know to work this out. I know that if I square this expression, this is the same as 9 to the power of 1/2 times 2. That's the nesting rule. So that's 9. So, because 1/2 times 2 is 1, so this is 9 to the 1, which is 9. So 9 to the 1/2 is the number where if I square it, I get 9. Well, that number is, geez, is it going to be 3? Because I know 3 squared is 9. So I could say 3 is 9 to the 1/2. On the other hand, I also know that negative 3 squared, well, that's just negative 3 times negative 3. And the minus signs go ahead and cancel out here. So that's also 9. Well, which is it? In this case, we're going to say that the answer is, we're going to say that the answer is 3. And that's just because if I want this symbol to make sense mathematically, it has to mean one specific thing. It can't refer to 2 different numbers. So we're going to say it refers to the positive one. This is called the principal square root. Principal is another word for positive in this case. So we're just going to go with the 3, not the negative 3. Another symbol to write that is the radical symbol. And that's that hook-shaped thing. I could write that the square root of 9 is equal to 3. So these two equations mean exactly the same thing. All right. So if I were asked, what is the square root of 49? We'd ask, what positive number multiplied by itself is 49? And that's 7. Now, what if I had something like root of 55? I don't know exactly what number that's going to be. I can't think of a number where if I multiply it by itself, I get 55. But I could tell you about what it is. See, 55 is bigger than 49, and it's smaller than 64. Now, 49 is 7 squared, and 64 is 8 squared. So if I have a number multiplied by itself that equals 55, that number has to be between 7 and 8. So I know that the square root of 55 is somewhere between 7 and 8. We'll look at some more tools in a bit to help us get a more exact answer. Now, what about other fractions? We've seen 1/2. Well, other fractions are just the same. For example, if I asked you what's the 5th root of 100,000, I could write that in 2 ways. I could write that as 100,000 to the power of 1/5, or I could write that as the 5th root of 100,000. Either way, I know that 100,000, since it's a 1 with 5 zeros, it's equal to 10 to the 5th. So 10 is the number where if I multiply it by itself 5 times, the 5th root of 100,000 is 10. Okay. If I asked you for, and this is a little special, if I asked you for the cubed root of 27, that equals 3, and that's because 3 cubed is 3 times 3 times 3 is 27. Now this is special. If I asked you for the cubed root of negative 27, that would be negative 3, and that's because negative 3 times negative 3 times negative 3 is negative 27. One pair of minus signs cancels out, but the other is left. See? So you can take the cubed root of a negative number, but on the other hand, we can't really take the square root of a negative number. If I ask what's the square root of negative 100, I can't really think of an answer for you. 10 times 10 is 100. Negative 10 times negative 10 is 100. To get a negative 100, we have to come up with a new kind of number. The answer will be an imaginary number. So we'll learn those next unit. We won't worry about those for right now. So we can take the cubed root of a negative number. Can't take the square root of a negative number. How about a fourth root? If I asked for the square root of 10,000, that would just be the fourth root of 10,000 would be 10, because 10 to the fourth power is 10,000. It's a 1 with 4 zeros. But if I try to get the fourth root of negative 10,000, well, that's just not going to work. 10 doesn't work, and negative 10 doesn't work either. If I take negative 10 to the fourth power, negative 10 to the fourth power, I get positive 10,000 because there's 4 minus signs and they cancel out in pairs. But if I wanted something like the fifth root of negative 243, that would be negative 3, and that's because negative 3 to the fifth power is negative 243. The first pair of minus signs cancels, the second pair of minus signs cancels, and there's a third minus sign, a fifth minus sign rather. It's the fifth wheel, it gets left out, so the whole thing stays negative. So that's what you do if you have a exponent like 1/3 or 1/4 or 1/5 or 1/2. What if I have something like 8 to the 2/3? This is a little tricky. What I can do here is use my nesting property. 8 to the 2/3 is really the same thing as 8 times 2 times 1/3. Or I could write it as 8 times 1/3 times 2. Either one, because multiplication is commutative. But what that means, let's say I did 8 squared times 8 to the power of 2 times 1/3. That would be the same thing as 8 squared to the power of 1/3. Well, 8 squared is 64. And I know that 4 times 4 times 4 is 64, so 64 to the 1/3 must be 4. Or if I had done this in the other order, I could say this is 8 to the power of 1/3 and then squared. Now, since 2 times 2 times 2 is 8, the cubed root of 8 must be 2, and 2 squared is 4. Like I said before, math is consistent, which means we're going to get the same answer no matter which way we solve the problem, as long as our solution is correct. This method might be better because I can take 8 to the 1/3, and it gets me smaller numbers. Like if I said, what is, I don't know, what is 81 to the 3/2? We could do that as 81 cubed and then to the power of 1/2, which means we're going to take 81 to the third power and then take the square root of that. I don't know 81 to the third power off the top of my head. That's some big ol' number. So instead, I could say, oh, let's do this in the other order. Let's take 81 to the power of 1/2 and then 3. So this is equal to 81 to the 1/2 to the power of 3. Or, well, the square root of 81 is 9. And 9 cubed is 729. That's the same answer we'd get over on the left, but this way I can actually do it in my head. So, you see, I told you that trick of switching the order of the exponent multiplication would be useful. I can write this nested in either way. So that's how we'll do fractional exponents. Okay. Want to see something crazy? Let's try to simplify this expression. 4 to the 2/3 times 2 to the 1/6 times 3 to the 3/2 divided by 2 to the negative 1/2 times 3 to the 1/2. Now these are some wild exponents, but I can still use all of my exponent tricks. For example, I can say that 3 to the 3 halves divided by 3 to the 1 half is equal to 3 to the 3 halves minus 1 half. So 1.5 minus 0.5, you guessed it, it's 1. Let's do the same thing here. 2 to the 1/6 divided by 2 to the negative 1 half is 2 to the power of 1/6 minus a negative 1 half. Well, if I'm subtracting a negative, that's the same as 2 to the power of 1/6 plus 1 half. 1/6 plus 1 half. We haven't had to do this yet this semester, but we'll have to do it again a lot. The way I add fractions together, think of this like I've got a sixth of a pizza, and then I've got a half of a different pizza. And I can't really directly compare those and add them. It's like apples and oranges because they're two different sizes. But I can say this half is really the same as 1, 2, 3 sixths. The way I get that is I multiply by a 3 on the top and a 3 on the bottom. So they cancel each other out. I haven't changed the value of 1 half. It's the same as 1 times 3 over 2 times 3. But that lets me say that instead of 1 half, it's 3 sixths. So we'll multiply the top and bottom by the same number to get a common denominator. That's the goal here, is that I've got a 1/6 here and a 3 sixths here. These are called a common denominator. And what that means is I can directly compare them. I've got 1 slice here, 1, 2, 3 slices here. So that's apples and apples. Altogether, that's 4 sixths. Now, both of those are even numbers, so I can cancel a 2 out of the top and bottom. My final answer is 2/3. So 1/6 plus 1 half is 2/3. So I'm going to rewrite all of this now. I had 4 to the 2/3. We didn't change that. I had 2 to the 1/6 plus 1 half, and we saw that that was 2 to the 2/3. And I have 3 to the 3 halves minus 1 half. That's just a 3. All right. Now, if you're feeling prosaic, you might think that's as far as we can go, but I'm feeling adventurous, and I noticed something special about 4 and 2. 4 is 2 squared. I'm going to take advantage of that. Look at this. 4 is 2 squared, right? So if I wrote 4 to the 2/3, that's the same as 2 squared to the 2/3. But these are nested exponents. The nesting rule says I can write that that's 2 to the power of 2 times 2/3, 2 to the 4/3. So 4 to the 2/3 is the same as 2 to the 4/3. That's fun. So I'm going to rewrite this expression again as 2 to the 4/3 times 2 to the 2/3 times 3. Oh, I love it when this happens. This is going to turn into a nice whole number because that's 2 to the 4/3 plus 2/3 times 3. 4/3 plus 2/3 is 6/3. 6/3 is just a fancy way of writing 2. 2 squared is 4 times 3 is 12. So this whole crazy here is really just equal to 12, but you wouldn't know it if you didn't have exponent properties. We came up with exponents as a shortcut for writing multiplication, but once we knew their properties, now we can do so much more with them. And all of those properties followed directly from the definition. I didn't have to assume anything else. I just had to know my definition, and I get all these properties for free. And they let me do these wild things like change this monster into a prosaic old 12. That's our final answer. Now, you're not going to have to solve a problem that tough on the test. I just wanted to showcase all of the different methods we've got. All of the rules we've learned so far, like the product, quotient, and nesting properties, they still work with fractional exponents. That's the moral of this story. All right. So done. Quick warning. If I write the square root I don't know, 9 plus 16. I want to be very, very clear that this is not the same thing as the square root of 9 plus the square root of 16. Well, root 9 is 3, right? 3 times 3 is 9. 4 times 4 is 16. But 9 plus 16 is 25, and you should recognize 5 times 5 is 25. And 5 is not the same as 3 plus 4. 3 plus 4 is 7. 5 is not the same as 7. So these are two different numbers. And in general, if you have root x plus y, it's not going to be the same as root x plus root y. Because remember, a square root, a radical, is just another way to write a power of 1/2, and you cannot distribute exponents over addition. Okay? So remember this example. Remember that root 25 is not the same as root 9 plus root 16. 5 is not the same number as 7. If you can remember that 5 is not the same as 3 plus 4, you should remember you cannot break a square root up over addition. And again, that's because we can distribute multiplication over addition. We can't distribute exponents over addition. What we can do is distribute exponents over multiplication. So this actually gets us somewhere really good. If I write the square root of, let's do an example before I write the rule. If I write the square root of 9 times 16, well, that's really just 9 times 16 to the power of 1/2. And I know that I can distribute exponents over multiplication because exponents are just repeated multiplication. So I'm going to use that distribution rule from 1.2 and say this is 9 to the 1/2 times 16 to the 1/2, which is 3 times 4, which is 12. And over here, I could have also said 9 times 16 is 144, and 12 times 12 is 144, so the square root of 144 is 12. That's easier, but the important thing here is there was nothing special about the numbers 9 and 16 that let me turn root 9 times root 16, nope, I just gave it away, root 9 times 16 into root 9 times root 16. This works with any two positive numbers. Have to be positive, can't take the square root of a negative number, remember. But no matter what numbers I have, this is a rule, that the square root of x times y is the same as the square root of x times the square root of y. And this is going to be tremendously helpful to us. We'll call this, how about the product rule? It's a different product rule than the other one. This is the product rule for roots. Just remember that. And here's why this is tremendously helpful. If I write something like square root of 500, well, gee, how big is that number? I don't know. It's pretty big. I know that 20 squared is 400, and I know that 30 squared is 900. So this is somewhere between 20 and 30, but how can I be more specific? Well, 500 is 5 times 100, or 100 times 5. I'm going to write it in this order. And I know from the product rule, the square root of 100 times 5 is the same as the square root of 100 times the square root of 5. I can distribute this exponent of 1/2 over multiplication. We all know that the square root of 100 is 10. So 10 times the square root of 5 is a much nicer way to write this number. We wrote it in terms of a simpler square root. These will come in really handy in a bit. See? If I were going to write something like root 36 times x to the 4th times y to the 5th, what can I do with this? First, I'm going to use the product rule to say that this is root 36, root x to the 4th, root y to the 5th. So this is a new example. The square root of 36 is 6. The square root of x to the 4th, well, think about it this way. X squared times x squared is x to the 4th, right? So this is 6 times x squared. We'll handle this other one in the next line. Root y to the 5th. There is something I can do here. See, y to the 5th, that's 5 copies of y. I could write that I'm going to get tired of copying this 6x squared over and over, but it's important to remember that it doesn't go away just because I'm working on a different part of the problem. I can write 5 copies of y. I can write it as 4 copies of y and then an extra copy. Okay? So this is 6x squared times root y to the fourth root y. And we already know root y to the fourth is y squared. So this is 6x squared y squared times the square root of y. And that's as simple as we can get that. If I had, say, a square root of 72, well, I know that 72 is 9 times 8, so that's root 9 times root 8, which is 3 root 8. But we can go a little further. See, 8 is 2 times 2 times 2. So this is 3 root 4 root 2, because 4 times 2 is 8, and the square root of 4 is 2. So it's 3 times 2 root 2, or 6 root 2. We could have done this all in one step if we had said 72 is 36 times 2, and the square root of 36 is 6. 2 different solutions, but math is consistent, so we got the same answer. Your goal is to pull out all of the square numbers you can from here. So we could pull out a 9 and then pull out a 4. Well, 9 times 4 is 36, so we could pull it all out at once and just pull out the 36. As much square numbers as you can. Up here, 36 was square, x to the fourth was square, and y to the fourth was square, but we were left with a y over. Here we were left with the 2 over. You want to pull out as many square numbers as you can to simplify a square root. Well, sometimes that can be dicey. So here's what we can do. If I ask you to simplify the square root of 12,150, that's nasty. What I'm going to do is factor this number to find out what kind of squares I can pull out. The number under the radical will be amplified when it doesn't contain any squares anymore. So I'm going to factor this guy. I'll write 12,150, and I'll make what's called a factor tree. What number do you know is a factor? Well, it ends in 0, so we know 10 has to be a factor. This is 10 times 1215. 1215 ends in 5, so I know that 5 has to be a factor. Turns out that 1215 divided by 5, well, let's see, 1200 over 5 is 240. 15 over 5 is 3, so that's root 43. I also know that 10 is 2 times 5. So I'm going to keep breaking down each branch of this tree further. 243, here's a fun trick. 2 plus 4 plus 3 is 9, right? The digits of the number add up to 9, and that means the number has to be divisible by 3. Anytime the sum of the digits is divisible by 3, the whole number is divisible by 3. So I know that a 3 comes out of this. Let's see, 24 divided by 3 is 80. So 240 divided by 3 is 80, rather. 3 divided by 3 is 1. So together we get 81. Now I hope you recognize that number. It's 9 times 9. And 9 is 3 times 3. The other 9 is also 3 times 3. What we've got down here are the leaves of the tree, where I can't go any further. These are all prime numbers. So I want to collect all these leaves, and this is the bottom of our factoring tree, is all these leaves. We've got 2. We've got 2 5s, and we have 5 3s. So 12,150 is the same as 2 times 5 squared times 3 to the 5th. This is called a prime factorization. Every integer has its own prime factorization. You can always factor an integer into primes. It's a handy thing to do. Here what I'm going to say is, well, I know that, for example, the square root of 5 times 5 is just 5, right? So if I have a 5 times 5 under the square root, that's going to come out as a 5 outside. And the same with a 3 times 3 and a 3 times 3. So I'm peeling out pairs of factors. This is the same as root 5 times 5, root 3 times 3, root 3 times 3, and then the only things left over are this 2 and this 3. So a 2 times 3 here. Well, that's the same as 5 times 3 times 3, root 2 times 3 is 6. 5 times 3 is 15, times 3 is 45. So it's a lot easier to work with 45 copies of the square root of 6 than it is to work with the square root of 12,150. So this is our simplified answer. Let's try another example. Let's say I had the square root of 72 a b squared c cubed. Maybe even pause the video, see if you can work this one out on your own. It's always a good idea. Pause the video, see if you can work ahead. Well, all right. Hello again. Let's check your work. I'm going to make a factor tree for 72. I might recognize its factors. I know we did it a minute ago, but 72 is 8 times 9. 8 is 2 times 2 times 2. 9 is 3 times 3. So 72 is 2 cubed times 3 squared. I'm going to pull out the factors of these variable expressions as well. This is 2 times 2 times 2 times 3 times 3 times a times b times b times c times c times c. Now, what can we pull out? I've got a pair of 2's, a pair of 3's, a pair of b's, and a pair of c's, leaving behind a lonely 2, a lonely a, and a lonely c. So, root 2 times 2 is just a 2. There's going to be a 2 outside. There's going to be a 3 outside. Root b times b is a b outside. Root c times c is a c outside. What's left inside is 2, a, and c. We can simplify this just a tiny bit. I'll write my final answer as 6bc root 2ac. And there we go. All right. We have a few more things to do. I want to be able to add, subtract, multiply, and divide square roots. Before I do, I want to show you an analog to the product rule. If I asked you what is the square root of 5/36, that's actually just the same as the 5 divided by the square root of 36. You can distribute exponents over division, just like you can distribute exponents over multiplication, because remember, division is just a special case of multiplication, where the thing you're multiplying by has a power of -1. So I could do 2 in-between steps. I'm not going to every time, but I could, and say this is root 5, and then a 36 to the -1, and that's root 5, root 36 to the -1, and that gets us to where we are here. See? So just like you can distribute exponents over multiplication, you can distribute them over division just the same. In the future, we'll just do these 2 black steps. Root 5 cannot be simplified, but root 36 is just a 6. So this is 1/6 of the square root of 5. Okay. Let's talk about adding square roots. The key here is going to be to combine like terms. Hopefully you've seen this in a previous class, but what I mean when I say combine like terms is if I had 2x plus 3y plus 4x, like terms are where we have the same variable with different coefficients. So the 2x and the 4x are like terms. 2x plus 4x is 6x. There's 6 copies of x altogether. Now the other term has a y in it. It's not alike, so we cannot combine it. So our final answer here would be 6x plus 3y. That's what combining like terms means. And combining like is how we'll do this. So for example, if I had 2 root 2 plus 3 root 2, that would be 5 root 2. See? Like terms. Just like 2x and 4x were like terms, 2 root 2 and 3 root 2 are like terms. So we get 5 root 2 because there's 2 copies here and 3 copies there. Okay. Whereas if I asked what is 2 root 2 plus 3 root 5, I can't go any further. These aren't like terms. So this is as simple as possible. We cannot simplify. Now, there's a wrinkle. There's a wrinkle. It couldn't just be as easy as combining like terms, right? What if I asked for root 2 plus root 18? my first instinct is to say, it's as simple as possible, right? So those are two different radicals. Not like terms can't combine. But 18 is not simplified. 2 and 5 are both simplified. 18 is not simplified because the square root of 18 is the square root of 9 times 2, which is 9 times root 2. See, I can split up the radical over multiplication, and root 9 is 3. So this is the same as 1 root 2 plus another 3 root 2. Combined like terms, that's 4 root 2. So don't be so quick to say there's no way to simplify. That's only true if the radicals are already in lowest terms. If they're not, there might be something we can do. Here's a goofy example. Let's say I have 3 times the square root of 80x minus 4 times the square root of 45x. Oof. Those don't look like terms, but I have a feeling we're going to get somewhere. Because neither of these is really simplified, right? 80 is 8 times 10, 10 is 2 times 5, and 8 is 2 times 2 times 2. So there are definitely some squares in there. So it's 2 to the 4th power times 5. And 45, well, that's 9 times 5, and 9 is 3 times 3. So there's a square in there as well. It's 3 squared times 5. As a matter of fact, that means if 80 is 2 to the 4th times 5, then root 80 is root 2 to the 4th times root 5, which is 4 root 5. Okay? And that means root 80x, well, there's just an extra x at the end. Root 2 to the 4th, root 5x, which is 4 root 5x. 45 is 3 squared times 5, and that means root 45x is root 9 root 5x, so it's 3 root 5x. So I can rewrite this expression. This is 3 times root 80x was 4 root 5x. 4 root 45x was, whoops, don't want that there, 3 root 5x. 3 times 4 is 12. 4 times 3 is 12. These are the same, so when I subtract one from the other, I have to get 0. They cancel out. So this didn't look like it simplified, but as a matter of fact, it was equal to 0. All right. I'm going to continue this video in a second part.